Okay, the electrical conduction system. Like I said before, it has to be committed to memory. An impulse to the pacemaker site is the SA node. It'll automatically depolarize, but it does have some influence from your SNS and PNS. But cells, let's say in a petri dish, would spontaneously depolarize. Okay, and that's one of the characteristics of pacemaker cells. So we have the SA node, and then we have interatrial tracts. So if we think about, if I can draw in here, the heart muscle. Let's say we have an SA node in here in the right atrium, and then we have your AV node here, sitting here. And we also, when this stimulates, we want atrium to contract first before the ventricle. So we want to take advantage of atrial kick. So we want these to these to depolarize first, and then to have contraction to push blood into the ventricle just before the large ventricles contract. So the atrium need to depolarize at the same time. So we have interatrial tracts, or a tract, and that one's called Bachmann's bundle. Okay, and then we have internodal tracts, and that because between nodes. Then we have a His bundle, and then we have a right and a left bundle branch, which travels down the interventricular septum. And then at the end, we have a Purkinje system where these tiny little tracts feed the bottom of the ventricle. So this is the superconduction highway, highly efficient, full of pacemaker cells, and the SA nodes fire spontaneously. But if we do slow the rate or something, an MI or some event or ischemia or electrolyte imbalance affects the SA node firing, then any place along here will fire. And that's when we looked at all the other arrhythmias in the course. Okay, so SA node, AV node, His bundle, junction, and then right bundle branch and left bundle branch, and then Purkinje system. All right. Okay, so we talked about the depolarization of a cell. And then I want you to consider that the whole conduction system here is composed of pacemaker cells that have a function and that will depolarize as well. ECG allows us the ability to place electrodes on the skin that can pick up the change or the electrical change that's happening on a cell level, but also you think about every single cell in the myocardium and along the conduction system depolarize. So really what ECG is picking up is the summation of all the depolarizations of all the cells as this wave propagates, comes down the conduction system and propagates, okay, from cell to cell to cell. Now, if this is the apex of your heart, here's where the impulse starts. It flows down over the atrium, pauses a little bit here at the AV node, and then continues to flow down here. but the direction is generally in this direction, down and to the left. And that's the heart vector. Okay, so the wave of depolarization, or the summation of every single one of the individual cardiac cells depolarizing, sums up into a general direction that we call the heart vector, which is down and to the left towards the apex of your heart. Okay, ECG is just electrodes placed on the skin that have the ability to detect the electrical change. And so it can see, if I put an eyeball here, right, it can see, and we're going to call this one lead 2. We look in this whole course from lead to a single lead, but it can see the wave of depolarization, okay? And then what it does is it translates those single individual electrical events, and the summation, then it sums all those electrical events, and it changes that into a tracing or a graph deflection. And in lead 2, because the heart vector is coming towards it, pretty much, this is the eyeball, and this is where lead 2 kind of looks at from, the tracing that happens on ECG is predominantly positive. And so the normal cycle is a P wave, QRS, T. Okay? And that's your normal ECG tracing, where this is your P wave, right? From the beginning of your P wave to the beginning of your QRS complex is your PR interval. And then the beginning of your QRS complex to the J point, or the end of your QRS complex, is QRS. Then your ST segment is here. And then QT is from here to the end of QT interval. Okay. Where the P wave is the initial atrial depolarization, the QRS is the ventricular depolarization, and the T wave is ventricular repolarization. Knowing that the atrium does repolarize, but because it's such a small event, if you consider the number of cardiac cells just in this area of the heart versus the thickness and the cells, the number of cells that are in this big chunk muscular section of the left ventricle, just the sheer number of cells, when they depolarize, this is going to be a larger electrical event than this one. And so the atrial repolarization is hidden behind this QRS. This is a larger electrical event, right? So this is the one that predominates.